Bruno Cuevas. And yeah, I'm based right now at the Universidad Politécnica Madrid, but as Nicola mentioned, most of this work has been done in my previous position at University of Wisconsin-Madison at the CHR lab. And before beginning, I'd like to thank for the invitation to give this seminar. I also congratulate Takashi for his great talk. So I've been following this seminar cycle for a bit, and I think it's a pretty good place to solve my research. I might have to warn you, I'm gonna be like theoretically shallow because my focus is mostly on some practical aspects of chemical reaction networks. I'm very passionate about chemical reaction network theory and practice, but mostly because I think like it has a great potential to be applied to a specific problem, which is the origin of life. The origin of life, it's one of the main outstanding questions for us to solve. And I feel like there are at least a couple good reasons why that happens. First of all, it's a pretty counterintuitive process. And second, it's not happening anymore, which means like we have to study the past to be able to understand this process. From the phylogenetic point of view, we can study like the sequences of the organisms that we find today on Earth. And we can try to reconstruct the past as far as we can, which is the bread and butter of the CHR lab where I did most of my research. And for instance, doing so, it was discovered pretty long time ago that there is like a common universal ancestor, this organism that we call organism or whatever it is that we call LUCA. However, the problem is like once we get there, like the analysis of sequences, like the reconstruction of sequences is kind of like limited. So we cannot go much farther from than that using this approach. Therefore, to really understand what happened before this LUCA, we need to look at something that is different than sequence that might allow us to understand any prior process that might have happened before. So I guess I don't need to tell you that chemical reaction networks are interesting, right? I guess we are pretty used to see chemical reaction networks, especially, for instance, in the description of metabolism. However, I also have, as Takashi showed before, actually we can describe many more things than simple like metabolic processes using CRNs. For instance, here I'm showing a network of translation. Oh, sorry. Oops. Yeah, a network of translation, which is considered an information process. And I feel like in the end, CRNs can be used to explain like anything, almost like anything we can come up with. So I think like that's why they might be a very good kind of universal representation to be used to understand the origin of life. For those reasons, I think that a complete understanding of chemical reaction networks in theory and practice might be the way to move towards understanding abiogenesis. In that process, it might be important to gather a few pieces, such as getting very good computational models that have predictive capabilities. Also, I think at some point it will be necessary to have ways to do high throughput experimentation. And of course, it's very important to keep in mind like all these concepts borrow from theories, such as for instance, the role of buffering structures that we were just introduced in Takeshi's talk. Today, I'll be talking mostly about the predictive computational models, which is like what I'm mostly focused on. So my starting point is the study of prebiotic chemistry. Prebiotic chemistry is a subfield of chemistry where chemists have been trying to produce biomolecules that we observe in today's biology without life intervention. And also trying to keep in mind, like to reproduce the geochemical context where life might have emerged. Right now, at this point, we can consider it's somehow like a 72-year-old discipline if we consider as its starting point the Urey-Miller experiments. And during that time, it has really accomplished a lot. Here I'm showing you a quite mesmerizing representation of prebiotic pathways that lead to current biomolecules. This representation is 7-year-olds now, so I guess like we could add many more here. But I think like you can get the vibe here that in the end, like understanding like prebiotic chemistry, I mean that the prebiotic chemistry can be pretty complex and pretty it can be pretty complex to navigate. So my earliest approach when I started working on this field like 4 years ago, coming from a PhD in machine learning for computational chemistry, was like trying to get some of these reactions and try to simulate chemical reaction networks by simulating ab initio, by making ab initio calculations and trying to compute reaction rates and so on, trying to embed everything on a chemical reaction network and trying to simulate where do we go from there. However, those efforts failed pretty quickly. There are like at least a couple problems here. Of course, first we have the limitation of the computational chemistry tools. This doesn't mean that there are not like outstanding groups doing amazing research from the computational chemistry perspective. But in any case, most of these reactions are at least, we can say, challenging to study using computational chemistry. But more importantly for me, I realized that there was another big issue, which is that there is not really a good reference. And what do I mean with this reference is that by training, I'm a computational biologist, and I'm pretty used to considering databases for most of the problems that I can come up with in biology. For instance, if I want to know what a given protein is doing, it's much more likely that I will just go to a database, in this case UniProt, and look for whatever that protein is doing, than that I will go and read, let's say, 6 papers to fully understand this protein. Maybe I'll do that when I already have an idea. Same thing might happen for chemical reactions, where I might go to Kech instead of trying to really digest all the literature about a chemical reaction. However, if I wanted to do this in the case of prebiotic chemistry, I didn't really have a way to do it because there is not really like a resource of information that I can simply access and get all the information from there. I might have to go and read 4 or 5 different papers from the same authors to try to understand the chemical hypotheses, the experiments, how they carried out, what are the results, etc. So in the end, really digesting prebiotic chemistry is not easy. Therefore, after this failing start, we realized that there was actually an opportunity here to try to fill this gap. So that for that reason, I built this database that I call ChemOrigins, which is trying to systematize, as I said, the future and the past of prebiotic chemistry research. The reason why I think that this approach might have some potential and might be useful for a lot of people is that, again, it might allow to organize the knowledge of prebiotic chemistry. Organizing the knowledge might be impacting in research, mostly by allowing researchers to try to avoid the burden to study anything that is prebiotic. Right? If we can just jump to the data instead of having to navigate the literature, we might just move faster, right? But apart from that, I think this is not just an effort to digest the literature and put it all pretty in a web page. It's also, I think there are new findings that can arise from this systematization. For instance, maybe we can lay new hypotheses, or maybe we can perform new computational analysis that we could not carry out before. So in a certain way, I would like that prebiotic chemistry resembles a bit like the way we usually work in molecular biology, where we have strong databases with a lot of information, and that's where we start doing our research. So the workflow to build ChemOrigins is nothing out of the ordinary, because there are already 70 years of research reported. The starting point of this database is actually just to curated literature, at least at this stage. Then the curation of the literature produces some annotations that are converted into digital data and stored in a graph database. And that the graph database is served to, like information from that graph database is served to the users through a pretty user-friendly web interface. So the starting point, as I say, is the literature annotations. There's like a lot of information out there, and we don't really need to reinvent the wheel here. The problem is, like, of course, the standard literature can be a bit complex. So in the end, I need like community efforts. I don't really have a team of people working for me to do this specific task. So these curators, that might be anyone in the community, even you if you want, even some of you. Well, these curators will take like pieces of literature. So for instance, like, I don't know, a paragraph, a figure of a given paper that they have read and understood, and they might want to convert that piece of information that is complex, that is has like different nuances and so on, into a machine readable annotation that has no ambiguities, and that can be easily understood by a computer. Here, it's very important for me to really specify the reactions. Like the reaction and the molecules in a SMILES format to allow us to do chemomorphomatic analysis. So then once we have built these annotations, these ones are uploaded to a Git online repository, in this case, a GitHub repository, through a version control system. So by doing so, what we are ensuring is that the database is controlled using the same techniques that are currently being used in open source code projects. So that way, if people can make contributions, these contributions can raise new issues. These issues can be solved in the GitHub page, or it can be people can make branches of the repository. Branches can be merged. So anyway, we can do like all the things that have been done in open source projects to curate this information. However, I'm pretty sure that most people will find like using Git and GitHub pretty hard. So that's why I've been also like trying to create like user-friendly interfaces, so users can just come and write down what they found and just submit that to the system without requiring them to use the Git and the GitHub and all these kind of things. Then these annotations will be converted into objects that we are placing on a graph database. And the reason why I chose a graph database and not other kind of like more classical graph databases is because in the end, I think like the graph representation of the data seems to me pretty natural. And one of the things that it enables us to do is to do like very powerful queries on this information that really like resemble in a certain way, like the way we think about chemical reaction networks. For instance, I think like there was a very good case on like, for instance, like the usage of expansion algorithms or maybe autocatalysis detection using these kind of like graph databases, which are like much easier to it was much easier to implement those than using other kinds of approaches. Finally, like the information that is stored in this graph has to be displayed for the users. I've been also working on a REST interface, so computers can also access this database, but that's lagging a bit behind because I mostly focus on the user end right now. So users can access ChemOrigins through like regular search bar. Also, there is like an implementation of a network expansion algorithm. And also there is like an implementation of models that might allow us to categorize prebiotic chemistry any way we want to highlight, for instance, like possible prebiotic pathways to produce a given residue or a given amino acid or a given chemical cycle, etc. Actually, I think like I might show you the page directly. So say this is can you see my screen? Can you see the Raful? Can you?
Yeah,
Can you?
we can see, but it would be nice if you full screen this. Yeah.
Yeah. Okay. That's full screen. Yeah. Okay. Now, can you?
Yeah.
Yeah. It looks less pretty on full screen, but anyway. Yeah. I'm only starting with like this web development. Anyway. So in the end, my idea is like this is the web page I created. As you can see here, it's I think it looks pretty, or at least that's what I think. It allows different kinds of search. For instance, here I'm looking for the pyruvate molecule. And as we can see here, once we look for a given molecule, we'll find like many reactions that are involved with that molecule. And also if the articles provided some proof of like, let's say the temperature at which the reaction was taking, what took place, or the pH or anything like that, that will be also displayed in these pages. We can also go to specific molecules and find all the information here. Then there is like a models list here. For instance, here I have a few models that I annotated myself, and models can be anything that we want. For instance, if anybody has a specific idea about a chemical pathway, you just need to put reactions together to declare a model. So here, for instance, I'm showing you like, in this case, like all the pathways that I gathered that will allow us to create a threonine. So as you can see here, these pathways will allow us to start from very simple feedstock molecules that we can find in prebiotic settings, such as hydrogen cyanide, to threonine through these different chemical reactions. And here we can access these chemical reactions. And finally, there is like the possibility of doing expansion, to run an expansion algorithm. That means like we will have a starting seed set of molecules. In this case, these three molecules. These are like the identifiers of those molecules. So we can just come here and run them. And what this will do is like to take these three molecules and see how many chemicals can we generate from these starting molecules. So that can be like a way to explore the chemical space spanned by different seeds in the prebiotic context. So now let me return back to, oh, well, there is also an annotation tool, but anyway, for the sake of time, I will just come back to my presentation. Okay. So far, I have annotated like manually around 300 reactions, which is not really a lot. There's a lot of work to do. But anyway, I feel like at least this project has got to the place where I can already see like some patterns emerging. For instance, here I'm showing like some models visualizations of different processes that are relevant in prebiotic chemistry. For instance, here I might be showing like all the different pathways we have to produce alanine through different pathways. In this case, this is more like a surface pathway, while in this case, this is more like a hydrothermal associated pathway, maybe. Also been displaying here the pathways that are related with the production of 1,3-oxazole-2-amine, which is like a very important precursor for nucleotides. And here on C, I'm showing something that might be like where I see like most of the potential of this database. In this case, by gathering all these chemical reactions that were happening in different environments, I realized that there was like a way to continuously go from CO2 to different complex molecules, in this case, glyoxylate and so on, through chemical reactions that have been reported in very different environments. So there is not really like any evidence that there is like a carbon fixation, prebiotic carbon fixation pathway, such as this one, but something like this might be happening. I don't know. So the important point here is not really like this specific pathway is happening, but there might be other pathways that might be found in this database that might allow us to explain like new pathways and so on that we might have ignored before due to this like scattering of the data and all that. So I think like that could be the biggest potential here. Rafael, how am I doing with time? Because I see it's already 10. Can I continue 5 minutes
Yeah,
more?
please. Yeah, no worries.
Okay. Anyway, every time that I explain this, I always have somebody in the crowd that is thinking like, okay, but what are you, why are you doing this? Because in the end, this is just like a tiny scratch on the surface of the incredibly vast number of possible chemical reactions, right? I think there was like this paper by Robert Hazen a few years ago. I don't remember if this was like 2 power 50 or 10 power 50, but anyway, it's uh, like the number of possible reactions that might be happening on the surface of Earth might be around that. So in that sense, why are we even building this, right? Of course, if the goal of ChemOrigins was to catalog each of these possible reactions, then of course this effort will be doomed. However, I think like we don't really, the same way like we have in a toolbox different tools for different purposes, I don't think like ChemOrigins is aiming to explain these 2 power 50 reactions, but more like those reactions that have been reported that have a specific interest in prebiotic chemistry and so on. However, that means like we still need like those other tools to be able to tackle like these huge, like the exploration of this huge chemical space. So for that, I think like it will be very important that we have first tools that might allow us to predict chemical reaction networks, and even more importantly, tools that might allow us to understand chemical reaction networks once they have happened and they have been like measured in the lab, to like tools that might allow us to give an explanation to what happened. So out of the last Upcycon conference, it was born like this collaboration with Tim Sokolsky at the University of Wisconsin-Madison. At that point, he told me that he had this experiment where they were like doing very messy chemistry, like mixing a few chemicals and doing a few processes in series that will like increase the chemical diversity. But of course, the problem is like, as it's been like mentioned before, like all chemical mixtures in the end tend to become a tar, right? A tar of many different substances. So it's very hard sometimes to like try to navigate those. So we come up with a few different tools, like trying to explain his experiments, mostly based on like chemical reaction generation by using chemical reaction rules. Creating these chemical reaction rules from smarts is not always easy, so we took some time like creating also a tool for trying to debug our own smarts. And then we put some effort on creating a tool that might allow us to take these chemical reaction networks that have been generated and try to match them with the experiment by using what we call here a pruning algorithm that we'll explain later. However, these tools in the end, like, I mean, there are other outstanding tools out there, and I'm very aware of that. But in any case, we thought like maybe these ones will have like this one might be useful for some other people. Like we put them on a very user-friendly format. So for that, I created another web server. If I might show it again, give me a second. So we just go to rule it. Oh, what's that? Rule it. Oh. Yeah. So if we go here to rule it, the Streamlit, it's gonna. Yeah. Here we have like different tabs where you can do a few interesting things. For instance, you can provide a set of smarts and give a set of chemical seeds and then run a chemical reaction network generation. But most importantly, you can run this thing we call like a prune. In the end, like chemical reaction networks that we generate in the computer might be very big, but in the end, they are like, including like many things that might not be relevant for the experiment, right? Many reactions that never happen because they're impossible, because their kinetics are too slow, etc. So in that sense, we consider that maybe we could try to take these complex chemical reaction networks and try to mass them to experiment. And for that, we generated an algorithm that is based on linear programming. It's very easy. And in the end, like what we are doing is trying to minimize the chemical reaction flows, like trying to minimize the chemical reaction flows on a network, like on a system where we have imposed positive flows on the compounds that have been detected, in this case for mass spectrometry, but they can be detected by any other method. For instance, in this case, this bright yellow node, and then allowing only inputs on the seed compounds and allowing outputs on all the other compounds. So that means like it's required to find the detected compounds, and all the other compounds can have like any flow in this case. So by trying to minimize the rates of the chemical reactions in this context, we were able to produce like very sparse chemical reaction networks that will take us from the seed sets that will be included in the experiment to the measured chemicals that are described by the chemical reaction network. So this is an effort that is still like ongoing, and we might go back to it soon because it's like we've been like doing other stuff for some time. Finally, I'd like to finish this talk by talking about this other last effort. In the end, like too many times we are talking about CRNs and life emergence, but one outstanding question out there is like, okay, what are the properties that CRNs should have to be representative of living organisms? It's like, for instance, like if we could mold a chemical reaction network, which properties will give it to give place to life? So for this kind of like inductive effort, we gather a bunch of different chemical reaction networks from different domains, and we've been analyzing some different statistics on them, such as for instance, the degree distribution of the nodes of these networks, or other properties more related to the micromotifs, or also like the chemical space that is spanned by each of these networks. And that is giving us a set of features that might determine the life-likeness of these networks. So this is like, right now I'm not working on any of these like on a full-time. I'm doing this as a bit of a side projects. But I think like there are like a few very interesting future directions that this might take. First of all, ChemOrigins is about to go semantic pretty soon. I'm working on a very big update that will allow to improve like the searchability a lot. Also, I was told by some experimental people like, oh, Bruno, your annotation tool might look cute, but actually we do everything, we live through the rules of Excel. So, so it will be very useful if you just have a feature to import Excels, and that's something I'm working. Then I always get this question nowadays, like, why don't we just use AI or LLMs to do the annotation process, or even to replace the whole database? There is also like some ongoing work on that, not to replace the database, because I think it's important to still have a database, but more like to improve the annotation using LLMs. And also rule it it's still like an ongoing effort. It's been paused for some time, but I think like there is like a lot of potential there. But I feel like maybe the most interesting point will be like a merge of these two approaches, like the database approach and the generative approach in the medium term future. So the way I see it, like ChemOrigins could be like a way to produce, it could be a way to store like the evidence and rule it, or something like the way to predict chemical reaction networks based on that evidence. And with all of that, I'd like to thank my whole group at the Culture Lab in the University of Wisconsin-Madison, especially Zach Adams, the University of Wisconsin-Madison, and also Tim Sokolsky, that has been like collaborating with me like all previous summer. And of course, all the people that gave me money to do my research. And that's it. I'll be happy to take some questions.